As you know, Elon Musk has announced a competition for the best technology for capturing atmospheric carbon.
To spur creative ideas for what is actually the smartest way to take the trillions of tons of carbon that we've removed from the ground.
I present to your attention a specific solution that I have prepared and I consider it the best possible. I'm sure you will not find anything better in terms of economic feasibility. Strictly speaking, all that I propose to do is just to help nature more effectively apply their own restoration work.
So, as we know, plants and marine phytoplankton are the main natural traps of carbon dioxide, and at the same time producers of oxygen. And, as we know, with an increase in plant mass, everything is still bad for us. It not only fails to grow, but every year the forests become less and less. But with phytoplankton, I think, and certainly not only I think so, there is untapped potential for growth. It is well known that the natural mechanism for the supply of nutrients necessary for phytoplankton growth is the rise of seawater. In this regard, many devices have been invented for lifting deep waters. In the overwhelming majority of cases, lifting devices are supposed to use the energy of waves or pumps. This turned out to be quite enough for the needs of fish farms.
However, all the devices that I managed to find does not work as I see it, and I think that pumps and wave devices are not suitable for planetary scale changes. In addition to their higher cost and low productivity, they also have fundamental limitations.
First, a large number of low-power devices will be required, which will create problems for maritime navigation. A large number of scattered devices will create a lot of maintenance problems. Finally, most importantly, they are not suitable for upwelling from great depths away from the coast, and this is one of the key conditions for success, which I will talk about a little later. The main natural source of upwelling is ocean currents. However, the upwelling zones are no more than 1/10,000th part of the world's oceans. In addition, only a small part of the energy of the currents leads to upwelling. Basically, huge masses of water circle on the surface and inside the oceans, without producing a pronounced uplifting effect. More stable, cold and slow streams flowing in the depths of the sea come to the surface mainly only in polar latitudes.
So, we have deep and surface sea currents, and I suggest using them. My solution for lifting deep waters is extremely simple.
In order to bring water from the depths of the sea to the surface, a water conduit is needed. From one end of the pipeline, the water rise should be provided by the incoming flow of deep water from the other end. Additional water extraction should be provided by the upper flow. The lower inlet confuser is directed towards the flow. For stabilization, the lower intake also has a bend in the direction of flow. The top nozzle resembles a whale's tail. Top nozzle is directed downstream and uses the ejection effect for drawing out. The upper nozzle provides efficient flow extraction and, at the same time, mixing with the upper warm seawater layer. The entire construction of the upwelling duct is a frame structure. The frame is made of prefabricated sections and has some positive buoyancy. At shallow depths, buoyancy can be provided by simple hollow internal cavities. At great depths, cavities filled with saturated hydrocarbons. For example, paraffin. Buoyancy can also be achieved by using lightweight load-bearing materials. This whole upwelling construction is fixed to the bottom by a system of anchors, cables, and floats, if necessary.
In principle, the resulting scheme can already work, but there are still a few problems that need to be taken into account.
In the middle and polar latitudes, where the temperature difference between the upper and lower layers is negligible, the thrust promises to be quite satisfactory. However, in equatorial waters, the column of drawn cold water can give significant resistance if there is a large difference in temperature compared with water at the surface. In this case, a heat exchange circuit is required. Heat exchange is carried out using a directed flow of warm surface water. In addition to lifting efficiency, heated water after lifting and stirring will be more efficiently retained at the surface and not returned to the bottom. Another technical difficulty is that the ocean environment can be quite harsh in terms of the impact of storm surges. We can certainly strengthen the construction, but the simplest solution is to place the nozzle below the base of the incoming waves. However, if the position of the nozzle is calculated taking into account the maximum possible wave height, it may be too deep, and the raised water will not properly reach the surface. Accordingly, a mechanism is needed to raise and lower the upper nozzle, or the entire construction, as an increase or decrease in the height of the waves. The simplest device that can be used for this purpose looks like a container with valves and bleed drains. The tank is filled in proportion to the increase in the height of the waves, and thus lowers the construction. A slightly more complex device is represented by a float system. One or more floats of sufficient mass are also provided with bypass and damping devices, allowing the float to easily rise up and stay in the upper position. From the top position, the float also pushes construction downward. The design with float has the advantage of less flow resistance. In addition, the float can simultaneously be a functional room for placing all kinds of equipment. The floats can be equipped with dispensers that additionally enrich the water with the necessary microelements and target phytoplankton crops. Also, it is possible to use hydrodynamic rudders and surfaces. Hydrodynamic rudders can provide the highest speed of control. However, a special need for such more complex devices is most likely not required.
Finally, let's say a few words about proposition and safe use.
In contrast to the wave upwelling devices, the upwelling duct does not have strict depth restrictions. It is possible to draw water from the Mariana Trench if the feasibility of such upwelling is proved. However, extraction from a great depth naturally implies higher costs associated with increased weight of the construction and increased complexity of installation. Heavy construction and placement in locations with significant changes in flow direction may require the nozzles to be provided with extended degrees of freedom for vertical and rotational movements. Additional guides, pivot joints and anchoring cables will also add to the cost of the structure. However, small changes in flow direction can be accommodated by structural compliance in the radial or axial direction. For this reason, it is also desirable to locate the upwelling duct in areas with the least flow direction changes. The weight of the structure can also be reduced due to the streamlined teardrop profiles that create the least resistance to flow and, accordingly, giving the least load on the bearing nodes.
At the same time, the most positive corrective effect should be achieved precisely at the distance from the coasts.
There are several reasons for this. Firstly, of course, the waters that are more saturated with nutrients are located at a great depth, which naturally implies some distance from the shore. Secondly, near the coast, the water does not need to be saturated with so much nutrients. There may also be a risk of nutrient overload, and this can lead to excessive plankton growth. But, most importantly, there are very extensive zones in the oceans that are almost completely excluded from the process of photosynthesis. These zones are located at a distance from the coastal zones of upwelling, and they are of the greatest interest. Figuratively speaking, these vast oceanic zones can be called water deserts. Phytoplankton is almost completely absent on the surface of these waters. Since phytoplankton is the backbone of the entire food chain, there is practically nothing at all living in these areas. Unless, of course, consider the ocean floor, which is a separate ecosystem. Colonizing of virgin water has several additional benefits. Controlled targeted seeding of the most beneficial phytoplankton species can be carried out. Even an insignificant sowing of target phytoplankton species under such conditions can lead to their very rapid growth, since the aquatic environment will not contain a large number of natural consumers of phytoplankton. As the backbone of the food chain, phytoplankton grows much faster. This is one of the key points, but not the only one. Controlling phytoplankton overgrowth in aquatic deserts is also fairly easy. The fact is that it is possible to mix nutrient-enriched waters with poor waters in various proportions. To do this, you can use devices that additionally dissipate or turbulize the raised water. Dispersion provides a guarantee of safety from the explosive growth of various phytoplankton species that release toxins that are dangerous to other marine life. Their concentration in water simply cannot reach any threatening values. Thus, it is possible to very flexibly regulate the growth and composition of phytoplankton. At the same time, we get the maximum growth with the minimum necessary saturation of water with nutrients. Roughly speaking, we get the highest efficiency. By carrying out phytoplankton colonization of aquatic deserts, it is possible not only to improve the composition of the atmosphere, but also to largely compensate for the anthropogenic load on marine life, restore populations of marine life. Recovery of fish populations is very important for a full balance. Populations of small fish that eat zooplankton are especially important. In addition to what has already been said, it is worth mentioning something else. Any technical device immersed in the marine environment is subject to fouling. Fouling is one of the main reasons for the failure of oceanographic instruments that are in the water for a long time. Some materials, such as glass rubber and some synthetics, are less susceptible to fouling. However, at present, special coatings are often used to prevent fouling, containing toxic substances of biocides, many of which are trying to ban their use due to the polluting effect on the ocean. Naturally, we would like to avoid additional pollution. More than 1,700 species of marine organisms can participate in fouling. However, almost all of these organisms feed on the same phytoplankton and zooplankton. Of course, if we place engineering devices in watery deserts, their fouling will be minimized. The surrounding water will simply not contain a nutrient medium for this. Accordingly, maintenance and corrosion of materials are minimized, which means that the cost of manufacturing and further maintenance will also decrease. It also eliminates the need for biocides.
But that's not all. Upwelling duct will reduce the temperature of surface water, and this, in turn, may affect the weather conditions.
The volume of uplifted waters will of course be insignificant if we consider it on a global scale. It also will not change the overall energy balance and will not affect the overall climate change in any way. However, it is well known about hurricanes and droughts resulting from local temperature fluctuations and excessive local heating of equatorial and subequatorial waters. By lowering the surface temperature at one time or another in certain areas, extreme climatic imbalances and the destructive force of hurricanes can be reduced. As a consequence, reduce the destruction of urban infrastructure, increase yields. In particular, it is possible to improve the survival rate of tree seedlings and to increase the volume of forests. In addition, upwelling ducts are perfectly combined with wastewater treatment plants. Debris catchers work much more efficiently in a stationary version than from oncoming waves. Thus, we get not only a more fertile, but also a cleaner ocean. Sumptuously, isn't it?
As you can see, I'm not suggesting anything complicated. The construction does not expose by strong dynamic and static overloads. Due to this, it is as lightweight as possible, but at the same time quite reliable.
The upwelling ducts does not contain power units, does not threaten marine life, does not require complex maintenance, does not create noise, does not change the landscape, and does not interfere with maritime navigation. The only possible difficulty that may arise is the deep-sea installation of a large-sized object. However, people have been building structures of this size for a long time and successfully. Humanity has already set up an incredible number of offshore platforms, each of which can weigh tens of thousands of tons and carry hundreds of tons of sophisticated equipment, residential infrastructure, and so on and so forth. An upwelling duct versus an offshore platform is like a balloon versus an airliner. With comparable dimensions, this is a much lighter and cheaper design, which will cost relatively cheap in production, taking into account the potential benefits. Currently, the operation of offshore platforms is carried out up to 2.5 kilometers in depth, and this is not just the construction of deep water facilities. Complex oil production equipment is operated at this depth.
Now, I will give you a preliminary calculation of the efficiency and cost of an upwelling duct comparable in size to a medium-sized offshore platform.
Let's start with the fact that with comparable dimensions, the weight of the upwelling duct will be at least 5 to 10 times less than an offshore platform of the same linear size and, accordingly, proportionally less than the cost of the initial building material. If a medium-sized offshore platform weighs about 20 to 30,000 tons, then an upwelling duct of comparable dimensions, depending on the materials used, will weigh from 1.5 to 4,000 tons. The overall dimension of the such upwelling duct in the upper horizontal plane will be about 40 to 50 meters, with an internal diameter of the conduit of 12 meters, and a length of the conduit of 1,200 meters. The maximum cost of creating and installing a single instance of an upwelling duct of the specified size, taking into account all possible costs, is about $50 million. When mass-produced, the cost will be cheaper. By comparison, oil platforms cost up to $1 billion each, and no one is complaining. Of course, there are no fundamental restrictions that prevent the construction of upwelling ducts of much larger sizes. But for now, we will build on the indicated values. The average speed of movement of water in the ocean is about 1.4 meters per second. In various local areas, the speed can significantly exceed this value. In particular, the flow velocity in the Drake Passage is about 4 meters per second. If we take some intermediate value of the flow rate within 2 meters per second and, taking into account possible losses, take the average value of the efficiency of water extraction as 36%, then with a 12-meter diameter of the conduit we get about 80 cubic meters of extracted water per second. During the day, 6,900,000 cubic meters of water will flow, and this will amount to 2.5 billion cubic meters of water per year. I ask you to take into account 2.5 billion cubic meters. This is the volume of clean bottom water raised to the surface. The volume of the mixed water composition will be much larger. Okay, 2.5 billion cubic meters of water falls into the optimal area of the photozone in the depth range, mainly not deeper than 50 meters, and mixing. The ocean surface area involved in photosynthesis, after a year of upwelling operation of this size, will be in the range of 200 to 1,000 square kilometers.
To fully appreciate how much it will be, mentally walk along the sea sand speed for 100 kilometers. As far as I can see, phytoplankton will grow in such an area of water.
The proportions of mixing water can be different, therefore, here we get a wide range of values. You may understand that as further calculations are made, the number of input conditions increases, and the conditional range of values obtained also increases. The growth and dying off of phytoplankton in water is a rather complex and dynamic process. As mentioned, this process includes organisms that consume plankton, exerting pressure on its growth. The life cycle of various phytoplankton species is very short, and from birth to death is estimated at several days, or even hours. In a short time, the volume of phytoplankton, in some nutrient-enriched volume of water, will reach a concentration in the range from 1.5 to 40 gram per cubic meter of water. The annual increase in the mass of phytoplankton, not counting other types of plankton, with the volume of fertile water obtained will be at least 1247,000 tons. To create such a volume of biomass, microorganisms borrow at least 960,000 tons of carbon dioxide and produce at least 700,000 tons of oxygen.
Which is also impossible to overestimate. Oxygen production is no less important than the utilization of the excess carbon dioxide.
According to some estimates, the planet as a whole produces about 500 billion tons of phytoplankton per year. At the same time, a number of studies indicate that over the foreseeable period of time, the total mass of the world's phytoplankton has significantly decreased due to a decrease in populations of marine life and other anthropogenic factors. No one can name the exact figure, since accurate studies of the mass of phytoplankton became available relatively recently with the advent of the corresponding measuring satellites. But most researchers nevertheless agree that, one way or another, the global mass of phytoplankton has significantly decreased over the past century. Some studies show that the annual loss of phytoplankton is about 1% per year. Although there are other data about short-term explosive growths of phytoplankton in the polar latitudes, sometimes accompanied by the death of fish populations. In order to guarantee a shift in the balance towards compensating for the loss of phytoplankton mass by, say, 1.5% of the world's total phytoplankton, 7.5 billion tons of phytoplankton must be produced annually. The required proportional number of upwelling units will not exceed 6,000 units.
Thus, no more than 6,000 installations will be required to ensure that the process of phytoplankton erosion in the marine ecosystem is stopped, and there is a chance that a much smaller number will be needed.
The cost of creating such a number of upwelling ducts, taking into account the reduction in the cost of mass production, is estimated at between $30 billion and $130 billion. From 30 to 130 billion, this is, respectively, the lower and upper limits of costs.
Wide range. But as you understand, there are a lot of introductory conditions for the calculations. However, even for the upper limits of cost is quite an affordable value, given the potential that can be obtained. For example, the creation of offshore oil platforms has already cost at least 5 times more expensive. Let's summarize what we get for this money. Firstly, significant uptake of carbon dioxide on a planetary scale. Secondly, oxygen production. Oxygen is also involved in the reduction of the hotbed effect and is essential for the respiration of all living things. I think that each of us want to avoid this state of chronic hypoxia. Thirdly, management of climate anomalies. Reducing the strength of hurricanes and droughts is also a very important bonus. Fourth, restoration of marine populations, including commercial fish. We get a more clean and fertile ocean. Fifth, well, of course, we get new jobs and lower cortisol levels for all of humanity.